Hi, my name is Alex, and my topic today is color operation for Linux color pipelines on AMD devices. And the agenda includes a brief overview of the color pipeline API and the DRM color operations we defined and implemented for AMD devices. And finally, an IGT KMX color op test that demonstrate the color pipeline API and the color operations. So what's a color pipeline API? So this was presented by Harry previously, but let me just do a recap. So it's a model prescribe a recipe for how to manipulate a pixel values to arrive at the desired outcome. And it's an API to allow user space to discover the hardware capability in a more generic way. And the individual DRM color ops object will be changed via the next property of the DRM color op to constitute a color pipeline. And as you can see on the screen, a color pipeline is attached to the DRM plan, and on the right is just a dummy example how a pipeline and the color operation can be. So we defined 6 color operations for the AMD devices. The 1D curve and the 1D LUT is for the degamma, shaper, and the blend transfer functions. And we also have the CTM 3x4 matrix multiplier and the 3D LUT for HDR. So what's seen on the screen on the bottom is a color pipeline for AMD device. And on the right is an implementation in the AMD GPU. And there is you can see there is a one-to-one mapping. So the degamma transfer function will map to the 1D curve. And the HDR multiplier will map to the multiplier color up on the right. And so is the 3x4 matrix and the shaper and so on. So I'll give some brief discussion on each of the color ops we defined. So the first one is the 1D curve. So a 1D curve is applied to all the color channels. And because we are basically just passing a number for the predefined function, so it just have a one field called 1D, curve 1D type, which is enum values. And for now, we define 6 1D curve, which is the sRGB EOTF, BT2020 OETF, and the PQ125, and plus their inverse functions. And the 1D LUT is pretty similar to the 1D curve, but it provides a way to pass a custom 1D LUT from the user space to the Linux kernel. And because we are passing a LUT, so we do need a size that define the number of the LUT entries, and also a data block that will be where the user space write the LUT itself to. And the reason to have a 1D LUT is because the 1D LUT is provide more flexibility than the 1D curve, so people can use whatever they want. And the CTN 3x4 color up, or as the name suggested, it passes a 3x4 matrix. And because the 3x4 matrix has a fixed in size, so we don't need a size entry. We just need a place, a data block that we can write the 3x4 matrix from the user space. And similarly to the multiplier, it's a simple multiplier that applies to the all color values. And it's 64 bits in length, and it's in the format of S31.32. And the final one will be a 3D LUT. A 3D LUT has it's more complicated, so it has 3 fields. Like the first one will be a list of the supported mode, and a 3D mode basically describe the 3D LUT itself, the format of the 3D LUT. And because a hardware can support multiple different modes, so we have to return a list of the 3D modes. The second is the mode index. Basically, it's an index pointing to a 3D mode that selected by the user space. And finally, the data. The data itself is a data block for the 3D LUT that user space will write to. And because we need to describe what the 3D LUT looks like, we also need to define 6 fields for the 3D LUT mode. The first will be the LUT size, which can be any size, such as the 9, 17, or 33. So in our example, we are using the 17. And the second one is the LUT stride, which is the stride for each dimension of the 3D LUT. The reason to have this stride is mostly it can extend the length of the table. So it's mainly used for the purpose of the memory alignments. And the third one will be the interpolation algorithm for the 3D LUT. And for what we are using the tetrahedron. And the color depths can be 8, 10, and 12. And the color format is specified by the 4cc values. So it can be, for example, XRGB 16 or XBGR 16. And this, of course, also depend on the color depth above. So if you are using temp 8 bits, you can just using the XRGB 8. And finally, is the transverse order for when passing and writing the 3D LUT. So basically, what it means is the XYZ axis of the 3D LUT. So it can be, for example, LUT 3D, RGB, then will be the X will be R, and Y will be G, and Z will be the B, or it could be BGR. So that depends on what you are trying to use. And this is just an example of how we handle the color up in the AMD GPU DM. So as you can see, there is a one-to-one mapping from the left, which is the color pipeline, and how we handle each of the color pipeline on color objects on the right. And because not all color up are to be used, so you can actually set a bypass for each color up. And the bypass can be set independently, but could be depending on the hardware as well. And finally, the IGD KMS color up is a test for testing each or multiple color ups. Because we have quite a few subtests in the color up test, but they are behaving in a similar manner. So for all of the subtests, basically take an input image like the one shows on the screen. And the test will generate 2 outputs. One is the hardware output, which it will read back from the write back. And the second will be the software output, which will be using the same color transformation, but done in the CPU. If the output image are the same or similar, then a subtest passes. And we also allow some margin of errors. I believe it's like 5%. Just because some of the, for example, the 3D LUT might not be they might be not one-to-one map. So there could be some of error margins. And this is the format of a subtest. So basically, you do have each subtest. You have a color format followed by one or more color operations. The format could be like, for example, 10 bits or 8 bits, and the color up will be like one of the defined one previously. So for example, if we have a subtest for the gamma test only, So, and we are using 10 bits, and they will be the first on the button. So XR30 and the sRGB EOTF. If you do need to do more testing, do a test for multiple colorops. For example, if you are going to do 3 1D curve, then you basically just append the 2 other colorops at the end of the test. And the IGT test will execute the sRGB EOTF for the gamma, and the invert EOTF for the shaper, and the sRGB EOTF for the blend. And for now, we have all of the color up tested in IGT. So you basically can have like 8 bits that's on the left and 10 bits that's on the right. They include the 1D curve and the 1D LUT, 3x4 matrix, multiplier, and the 1 3D LUT as well. What's shown on the screen is a struct for the 3D LUT in IGT. So on the top is the 3D LUT. They will be passed from IGT to the kernel. And the middle is the 3D LUT mode that describe the 3D LUT. In this example, we have a LUT size, so that means we are passing a 17 by 17 by 17 3D LUTs. And the interpolation will be the tetrahedral and so on. And on the bottom is a function that we are using for CPU to compute the same software image, and then we can compare the two, just like I said before. So what you are seeing on the screen right now is the workflow between the IGT and the Linux kernel for the 3D LUT. So first, the IGT will initiate a game mode, where the Linux kernel will return a list of the supported mode by the hardware or by the driver. Then the IGT will match the one I just showed, will match its mode, and pick the one that has have the exact match. And then you will write the index that pointing to the mode. And the 3-step complete the mode selections. And the IGT is now able to write the 3D LUT followed by the frame buffer. And then you can read back the frame buffer from the write back. And then you will take the output and compare the one we also compute from the software by the CPU. So the 2 images will be compared and generate a pass and fail. Yeah, and so that's pretty much everything. So both of the Linux kernel patches and IGT patches are sent to the mailing list. So if you want more detail, you can also check out the mailing list as well. Yeah, so that's about my presentation. Any questions?
Hi, is any of this available to call through DRM so that a compositor or something like that could implement any of this hardware features?
Yeah, I think so. Yeah, they are called by the DRM.
Okay. A second question. I have actually a little bit of experience implementing some of this. So I am a W-rich contributor, and one of the things that one of my recent contributions is implementing software for transforms. So 3D LUT, like you were talking about, where you have a 3D texture and you just map a color in and you get another color out.
Yes.
So one of the things there, one of the benefits of doing it in software, not on the CPU but as the GPU shader, is that you only need to recompute the color transform for the damaged regions of the screen. So if you only have a window that's in a corner, you only have to, in software, you can only recompute the color transform for that corner. But the problem is with hardware, does that computation happen every time the screen scans out? Is there some sort of way that actually software using a GPU shader would be faster than using hardware if depending on the screen size that is changed?
I think it's always done. There is no. Oh, yeah, Harry.
Yeah, just some comments. It doesn't matter because this is fixed function hardware. The pixels go through the pipe no matter what. Powering on a 3D LUT takes a bit of extra power, but once it's powered on, the pixels will just flow through, and it doesn't matter. Like it's always the entire thing. Pretty much, right? We're not using a shader to compute it in hardware. We're using fixed function hardware. That's why that's where the benefit comes in. You can leave the graphics portion off, and that can save you a lot of power.
Okay, and one last question. Some of these 3D LUTs can actually be quite large because it's the 3D.
Yes.
It's in 3D. So if you increment one dimension, you allocate a lot more space. Suppose you already had an allocation through Vulkan or whatever for the memory. Is there some way to reuse that memory for the fixed hardware, or you have to send DRM, a pointer on the CPU?
So for now, I believe you have to always send it. But in the future, as long as the hardware is supported, we can create another color up that support passing the 3D by reference. Yeah, it's definitely possible with the interface, but not right now, not in the current implementation.
Okay, thank you.
Hi, thanks for the interesting talk. I just had a quick question about the KMS colorop test. So how are you doing the comparison between the write-back output and the software buffer?
Sorry, by the one captured from the write-back. So that would be the output from the hardware, and we take the output, the input image, and do the same computation by the CPU, by the software, and generate another one, and we do the comparison between the two.
Yeah, so I was just wondering how the comparison is done. Is this via the existing FNV1A CRC helper?
Well, basically we compare pixel by pixel, but with the range of margin, could be 5%, I believe, or something. So nothing fancy, just the value comparison.
Got it.
Yeah, and a brief comment on the CRC portion of your question. The reason why we're doing pixel by pixel comparison is because hardware and some of these algorithms might have off by ones. As soon as you're off by one, your CRC is wrong. You don't know if you're close or if you're far and get complete garbage, right? And to understand whether you're close, you really have to look pixel by pixel. Are they within a small amount of margin?
Yeah, thank you.
Got it. Thank you.
Quick question. Is there any, maybe, unless I missed it, is there any work on the testing of the blending of multiple hardware layers in this path? Or is there actually support for hardware layers on this hardware? What's the
blending of the multiple planes, you mean?
Yeah, you would have different planes with different color space that goes out with a certain color space, yeah.
That's a good question.
Okay.
Well, no tests for that yet.
No.
One could create tests for that using IGT. Using the same approach, you could just, Control-C, Control-V, the existing test, create your two planes and get your write back and compare that to a software model of the same thing. I think what you're getting at is, right, how is blending done, and, how do we define what
it's a very desktop thing, right?
Sorry?
It's a very desktop thing to blend.
Yeah, I mean, it's an important question.
Right.
We haven't created a test for it. Somebody could if they wanted to. It's an important thing to look at.
Thank you.
Thank you.
To be fair, if you test the correctness of each plane, the blending is hardware specific anyway.
The question is loaded. There's many decision and trade-off that you're gonna do in the middleman between your input, the blending engine, whatever it is on your hardware, and the final output. So you can do the full mathematical perfect operation where you go back to very high depth linear representation, or you can cut corners.
But the reason this API is defined as a prescriptive model is so user space, like a compositor, can understand what's happening, right? the way a compositor programs this pipeline, they should know whether they will be, for example, in linear space for blending, or in PQ space, or in some extended sRGB or normal sRGB space, etc. Right? You could model this directly through GPU shaders and then do the same through your display hardware. And at the end of the day, the display driver doesn't know the blending space. It just knows I need to do this and this and this to my pixel. Then I'll blend them together, and then I do something else.
I'll just add one. Is AGT planning to add support for external acquisition for the case where hardware where you wouldn't have actually a write-back connector?
It's not done yet. I mean, theoretically, you can do that. I know Google has put some convenience that you can capture the output, but it's not. You can do that, but it's not done yet.
Yeah, there's Chameleon being dispatched in some of the labs now. Yeah.
Yeah.
Okay. Thanks.
Thank you. Any other question? No.
Which compositors do you expect will actually use this color pipeline, and under what circumstances would there be a color transformation to actually do? And also, for the stuff that really cares about color accuracy, will the fixed function be good enough, or will they have to use shaders anyway for precision reasons?
So I already have an implementation for Quinn where we can, right now in full screen only, once we have more overlay plane usage, whenever we scan out a video, for example. About color accuracy, if you want accuracy, you don't want to use that at all, pretty much, because the results are just slightly different from more exact calculations that you do in a shader.
Okay, so like movie studios and such will just be doing everything in shaders.
Probably.
But so what kind of color changes would Quinn be doing?
For example, if you have an HDR video but an SDR screen, we can do tone mapping with a 3D lookup table, or change the gamut of the video, change the transfer function, those sort of things.
I think it's important to understand that this is mostly for the playback of content, not for the production of content. And why it matters is because most of people uses a battery to playback. And this is where you actually save on power.